So today's talk is going to be about finding hidden memory issues in Postgres. Um, so this is going to be a 40-minute talk. We'll have the talk for around 30 to 35 minutes, and we'll have a question and answer session. So we'll have some introduction initially. So I'm a database developer at Zoho, and I work mostly on DB internals, mostly focusing on storage and execution. I also look at the performance angle aspect of things. We are mostly focused on extending PG for our org's workloads. So about a word about my organization. We have been in business for around 30 years, and we have a presence in around 150 countries. I developed our 60 plus apps. We are an employee count of around 19K people. Okay. So just to set the outline of the talk, so we'll look at what memory contexts are and what the lifetimes and how a bit about what hierarchical allocation is about. And we look at memory defects and why these issues can be hard to reproduce. After that, we'll look at a testing mode which can make the AddressSanitizer signal more effective. And finally, we'll look at few bugs that we have found between PG version 16 to 18. And we'll conclude with the takeaways, right? So we'll start off with this small code snippet. Can any of you figure out what the issue here is, or what the output of the program could be? I have freed the char pointer, but this is a perfectly valid program. But can you guess what the output is going to be? Okay, so someone told A. It could be anything actually, because this is basically an undefined behavior. So what happens here is, you do allocation, you do a free after this allocation here. You do a free in the line 12. Post that you do a setting this A to that 0th value, right? So what basically happens is, based on your malloc, the implementation under malloc, this program could either crash or it could print A, right? So this kind of behavior is undefined both in C, and this as well. This is also undefined in PG also, right? So just an intro about PG. As you know, it is implemented in C. It is performance oriented, and is also complex. So these memory issues, for example, I am just sticking to 3 issues in this talk. 3 main issues are use after free, buffer overruns, and double freeze. So these issues are actually very hard to figure out inside if it happens inside Postgres. So the problem initially, just like any other C or C++ code bases, is that these problems exist, these undefined behaviors exist in memory, but it is very hard to reproduce these issues, right? So what are memory contexts in Postgres? So Postgres memory context is basically an infrastructure that PG provides to group your allocation. So also you can have your workload specific allocation under the memory context. So like any C code base, you don't instead of spilling the malloc and free calls all over your code base, what you could do is you could arrange it under a single context, right? And the context itself form like a tree kind of a structure, and the cleanup basically happens mostly happens in bulk using a reset or a delete API. Now the reset is going to clean up everything, and but the context itself. Delete is going to delete the context as well, and this could be considered both as a performance and a correctness mechanism, whereby you basically free up all the resources correctly. So the image besides depicts how generally memory is allocated. You have a bigger chunk allocated and you have smaller chunks given to the program when it is asked for. So next is about lifetimes. So this is basically, the image basically depicts a top-down view of the context, basically how it is structured in PG. So you have the top memory context, which is the longest lived context, and inside that for every transaction you create a top transaction context, you have a portal context for the query evaluation, then you have a executor state context for executing the query, and then you have a per tuple context. Sorry. So as you go down the lifetime of the context itself shrinks. So the per tuple context lifetime, it is going to be reset multiple times inside the same, during a executor evaluation. And the executor state context is going to be reset for every query that is getting executed, so on and so forth. So any pointer that is getting getting freed in the inner context becomes invalid, right? So this also helps coupled with PG's exception handling. What it will help in doing is when you have an error getting thrown while evaluating a tuple, what happens is the control can go to the PG catch and basically it can free up the children behind right. So that way PG basically helps us, its developers use allocation safely, and you could also use exception handling inside PG code base. So just like any other mature C code base, PG manages its own memory allocation and workload, right? So these are the 4 different allocation strategies that we see in Postgres. The AllocSet context is basically the most commonly used general purpose allocation strategy, and it is very similar to the libc implementation or JMalloc implementation also. It basically uses freelists and reuses memory when possible. Generation context is FIFO, it does FIFO kind of allocation. It is used for specific workloads. Slab allocation is used for when large fixed size allocations are needed. Bump allocator is like an append only kind of mode, which is used in sort and some other areas. And so in this talk we will just stick to AllocSet because it is going to be the it is a general purpose allocator, and it is mostly used in Postgres. So AllocSet implementation is mostly kind of how the general purpose allocators also work, and just like general purpose allocators, AllocSet also have doesn't enforce pointer validity or bound safety, right? So this causes all the 3 issues that I have said before: the buffer use after free issue, buffer overrun, and double free. We'll look into these issues later on in the later on slides, but these issues are not specific to PG's allocator, but it can happen to malloc implementation also, right? So before we proceed, normally how C++ code bases mitigate these kind of memory issues is using something called AddressSanitizer. So AddressSanitizer is a compiler instrumentation that can detect memory issues at runtime, right? So this can basically figure out all these issues that I have just discussed. So it basically relies on free realloc APIs. So free is going to poison your memory that is getting freed. The ASan will mark red zones around mallocked areas. So the overhead of using this is kind of like around 2 to 3x. So 2x around CPU and 3x costly on the memory. But it is basically practical enough to run your regression suits and your testing. And the problem with ASan is it doesn't work well with PG. So unlike the general purpose allocator, which directly takes your memory from OS to put it in simple terms. PG basically works on top of the malloc itself. So basically the free list, so if you can see in this diagram, normal allocator, it will free, ASan will poison the memory, but it will crash on your next access. But in case of AllocSet, what is going to happen is your pfree could free it, but sometimes it could put it in the free list also. In this case, the memory is still accessible, and ASan is basically blind on this. So we'll discuss a bit on these issues, going on how this happens, and in case of AllocSet. So the first is the use after free. So mostly, as in this is the same thing that we have discussed in the previous slide. So when pfree is called, the chunk is basically put back into the free list. So basically the pointer is still valid in this case, and the person, if someone is holding on to the pointer, he'll be able to still use it. And this makes the this creates an undefined behavior because this pointer can be given to some other guy calling him payload, right? Now the other problem that you have is buffer overrun. This problem happens when your write basically spills out to your next chunk. So in the initial slide, we told like memory context inside, you will be allocating in blocks and like giving out memory in chunks. So suppose you have one chunk writing across its boundaries, it could spill out to the next chunk, as shown in the video, as shown in the image. So in this case, basically there is no block boundary that is getting crossed here, and in this case also, no segmentation fault happens, or ASan is also blind on this, right? So this double free is basically another problem that can happen. So here what happens is, suppose pfree is called, pfree is a freeing API for the memory in PG. This guy could basically put your chunk back into the free list twice. So what can happen is subsequent payloads could receive this same address and use it differently, which could basically lead to data corruption. Right. So before we go ahead and rewrite PG in Rust, we could look at memory safety tooling what PG offers now. Right. So we have a set of macros that we can use to kind of help us in this issue, right? So first is the memory context checking macro. So this macro, you can enable all these macros while compiling PG itself. You can adding it as additional extra C flags. So this macro basically what it does is it will put a sentinel bit after each chunk, and it will also hold your request size along with the chunk, so that during a memory context check happening after a transaction, it could figure out if there is some corruption happening. Now, the randomized allocated memory macro. So this macro basically what it does is it will fill your newly allocated memory with 0 ASan. Basically it will set all the bits to 1, and this will basically lead to the subsequent reads returning garbage values. The other thing that we have is Valgrind hooks. So you could compile PG with Valgrind hooks and run PG on top of Valgrind. So this will basically mark all your allocations, and it can help you figure out issues during when it is getting run. Though the problem with Valgrind is it's extremely slow to run your regressions or any tests on it. Just putting all these tools in a single slide here. So you have memory context checking which can detect pass chunk end, writes pass chunk end, but this is detected only at the end of the transaction, and you wouldn't actually know exactly where it happened. The other thing is randomized allocated memory. This can flag uninitialized read, but this doesn't help in other cases like UF or buffer overruns. The global free memory could help you your reads getting flagged out because of wrong values, but the chunk basically stays in the same address, and you could basically write into that address without any problems. Valgrind is basically can figure out all these problems, but it is way too slow for running regressions. Now, AddressSanitizer is basically useful, but in case of Postgres, what happens is it is basically basically blind to freelist reuse. And there is something else that PG does. It might have some padding during allocation, and these are also blind to that also. Right. So this is basically a solution that we came up when we faced this problem. So we wrote a memory context, not for performance, but for testing and finding these kinds of memory bugs. So now in this memory context, what we are trying to do is instead of marking, in this memory context, what you have done is we will just map your malloc free and realloc APIs directly into your context table. So, and this will be enabled by default when you are compiling PG with enable CSet. So when you compile with enable CSet for all the allocator implementations, you will just enable this instead. So why not basically use ASan API and do manual poisoning? So we don't want to spill the ASan API all over the code base because you already have Valgrind to do that. And this basically helps you leverage on ASan's native malloc free and realloc hooks. So if you look at it, the palloc and pfree will basically look at the memory context table, and it will figure that the context is a malloc context, and it will call libc and libc is malloc and free. So this will basically aid the AddressSanitizer. So the slides presents how the design is and how it is integrated. So PG's core memory manager dispatches operation through method table. So the method ID is basically stored in the stung header. You have the alloc free realloc route to the correct implementation by the method ID. So now what we have done is we have added this new context to this existing table. A bit about the internals. So every allocation we will have a small header. So this header will have the size of the allocation, a dlist node, and you will also have the pointer to the actual context. The context basically keeps track of all the allocations that happen using a dlist. So suppose a alloc is happening, what we do is we do the allocation plus the header. We push this into the memory context dlist. So you can see that how it is not performant enough. But on the other side, each allocation will basically only have what it is allocated for, and the AddressSanitizer can correctly poison and mark the red zone for each and every allocation. Right. So we don't actually perform complex regression testing or stress testing on PG. So all the bugs that we are going to discuss has actually come up with just running standard regression suite with this particular context, right? So all these bugs have come in between PG16 to PG18. Some of these we could reproduce. We could crash the system or return wrong results. One of these we can do like that. Others we are not able to deterministically kill the system because the behavior of the system depended on what AllocSet did. And but these issues were actually visible in the code, and this was confirmed and fixed upstream. So the first bug that we had was an issue in window aggregate. So I have attached all the references to the PG hackers link in this slide, and we'll upload it into the talk section. So this issue was basically a use after free problem. So in this case, what happened was window aggregate transition, where you actually compute the transition has actually a pass-through mode. So if the run condition basically fails, you reset the perturbable context. So in this case, what actually happened was the reset basically pushed your pointer into the free list, and the subsequent exec project tried to work on top of the same memory. So this actually we were able to crash the system with a query actually, and this bug was fixed upstream. So the next two issues happened in parallel vacuum. One happened in the parallel vacuum worker and the other in the leader. So this is the one that happened in the worker. So here what happened was you were destroying TID store and recreating it, but the subsequent code basically used the stale pointer. So we couldn't predictably clash this system, but with malloc implementation we were able to exactly point out where the allocation happened, and they point to the exact issue. And this issue was also fixed upstream. In case of malloc context, what happened was the new address was assigned and the old destroyed address was marked poison. So we are able to the AddressSanitizer basically flagged this problem. So this is also happened in vacuum code, and this is also similar to the previous issue. Here the TID store was destroyed and recreated, but the leader process basically, instead of calling the new pointer, it still accessed the old pointer. And why it is in case of alloc-set, like I said before, the free and alloc basically return the same pointer, and the malloc basically return different pointers and mark the freed area as poison. Now, unlike the initial example that I showed in the talk, where you had a free happening and then you write to the area, since you are able, someone who is a C developer could actually see it. But in case of PG, what happens is these alloc and free code could be separated by, could be in a different file altogether, or it could be separated by a large chunk of code. So it is not actually very easy to figure these kinds of issues out, right? So now I would like to discuss why AddressSanitizer output is actually very much valuable. So in case of a generic segmentation fault, you know something bad has happened and you get a stack trace. But in case of an ASan report, you get 3 detailed information. You get the allocation stack, you get the deallocation stack, and you get the access stack, exactly where the problem happened, where the deallocation happened, where the allocation happened. This actually means that you don't have any false positives, and every report here is basically a logical error, right? So if you are using an AI or something, you could just give this stack and it can actually accurately fix the issue. So this, as I said, the stack trace basically pinpoints the fix. So a practical way to use address sanitizer report is to, especially in case of PG, is to identify the allocation context and find its lifetime. Then see where the pointer is actually deleted or resets. Then once you do this, then the fix could be as simple as moving the pointer allocation to a separate context, or you could nullify the pointers after free, or you might need to reroute the control flow to fix the problem. So I'll conclude the talk with the takeaways. So these kinds of performance degraded testing modes are actually a worthwhile investment. So this will help us figure out these kinds of memory and undefined behaviors. These most of the memory defects are lifetime defects, and this kind of malloc mode is a very easy way to figure out bugs. And using this, you could actually enhance the visibility of the issue in your existing test itself. Your existing test could actually be a good enough suite of tests, but it could fail in figuring out these issues. But with this particular mode, you could actually unmask the issues. So